Okay, I'm not going to try. Is it going?
Yeah.
Okay.
Yes.
Okay. So then we use the conformal transformation under dilatations to read off the quadratic singularity. And then we use the transformation under translations to read off the next singularity. So this tells you what happens when a stress tensor comes near a primary operator. Okay, so we're gonna use these equations a little bit later. There's one more equation, which is an example of this. That I want to get on the board so that we can just refer back to it later. Okay, and this is the 3-point function of a stress tensor with primary operators. Okay, so T of Z, O of W1, O of W2. So I claim that this is completely determined, this function is completely determined by its OPEs, okay, by its singularities. Okay, and I'm going to explain why that is. So we know that if we bring Z near if we bring the stress tensor near this operator, then we know the singular behavior in Z minus W1. So let me write it out. It's H over Z minus W1 squared, and we also have this operator here, so I'm just plugging in this operator product expansion. So there's OW1. I'm going to stop writing the W bars, but these are not holomorphic operators. They also depend on bar. Okay, so we get this. This is the leading singularity for Z near W1. Then we get that subleading singularity, which is 1 over Z minus W1, dW1, O of W1, O of W2. Now, we also get the similar terms from bringing Z near W2. Okay, so there's terms where you swap W1 and W2. And then there can be non-singular terms. Okay, because the conformal transformations only told us about the singularities in this correlation function. So how are we supposed to figure out the whole function just from knowing its singularities? Well, it's a holomorphic function of Z. The function we're looking for is a holomorphic function of Z. And if you know the singularities of the holomorphic function, then you know the whole thing. Okay, so in fact, we know that these are the important thing is that we know that these are the only singularities of this function, including at 0 and infinity. Okay, so no other singularities on the complex plane or at infinity. The only tricky part of this is what it means to be regular at infinity. So let me explain that. Well, first I'll tell you what it means to be regular at 0. So regular at 0 means that if you expand near 0, there's no singular term. That's pretty obvious. Constant plus number times Z plus dot dot dot. So that's pretty obvious. But now we can get regularity at infinity. So to get regularity at infinity, we change coordinates from Z to 1 over Z. So define X as 1 over Z. Then Txx of X is dz dx squared tzz of Z. which is x to minus 4 tzz of z, or z to the 4 tzz of z, which means that if we want the stress tensor to be regular at infinity, then that means we want this thing to be, we want the leading term in the expansion of this near 0 to be a constant, which means that we need tzz to go as 1 over z to the 4. Okay, so when you say it's regular at infinity, this means that t of z goes as 1 over z to the 4 as z goes to infinity. With that subtlety out of the way, it's now pretty straightforward to check that this function is uniquely has now been uniquely determined. So I'm not going to go through the rest of the algebra, but it's completely determined by this fall off at infinity and having these singularities. And the function itself I can then write down so that we can refer back to it in a couple lectures. It gives t of z, OW1, OW2 is h times W1 minus W2 squared over z minus W1 squared z minus W2 squared. That has all the singularities and it falls off as z to the 4th, so that's the answer. I guess I should say that 3-point functions are always determined by conformal invariance. It's not a surprise that we were able to do that. That's true even of 3-point functions in higher dimensions. But by using holomorphicity, it was easier in 2 dimensions. We didn't have to go thinking about, we didn't have to really go thinking about special conformal transformations in detail. We just used holomorphicity and there's the answer. Okay. That's it. 2D CFT is done. We know everything about 2D CFT. I recognize that some of this went kind of quick, and I think a lot of people found the problems difficult. Don't worry about it. Don't worry about it. We're going to use some of these formulas, but if you haven't seen it before, it takes a while to absorb this stuff. If you haven't seen it before, it's fine. We're going to use this formula, and we're going to use the word identity, and the conformal transformation rules, but that's about it. A lot of this other stuff, I just thought was fun, so I told you. Okay, any questions before we go to the next topic?
I have a question.
Yeah.
So we can insert a stress tensor into like an endpoint correlator, right? Just like how we did for the 2-point. There also we know all the similarities and the follows.
Yes.
But I don't think we can write a closed form like this, right?
Even in 2 dimensions?
I don't know. I'm asking.
Well, so we don't have, no, well, if we knew the endpoint function of operators, then we could write, we would also be able to write down the expression with the t in there. Now, it was essential in this argument that when I did the OPE, I got a 2-point function, and I knew the formula for the 2-point function. So we got a closed formula. More generally, you would just reduce it to an endpoint function, and you would know how to calculate that, so you wouldn't get a closed formula.
Yeah, so that means we have not like reconstructed it just using singularities and follows, right? We have solved, like we have acted a known function by a differential operator, and then we got this.
Well, I think you could say it either way. The point, this singularity, as an operator equation, this singularity has an operator in it. Okay, so in this case, that wasn't a problem. So we were able to find the singularities of this function as functions. We were able to write them down because we knew the 2-point function when these got contracted to an O or a DO. Okay, so that was the first step in the calculation, was to find the singularities of this function. And then we were able to complete the calculation. If you do this for more points, then we know the singularities of this OPE, but they have operators in them, and we can't write down the singularities of this function. Any other questions? Okay. The next topic is getting back into quantum information. And I'm going to start by discussing general properties of quantum entropy. Probably we'll spend the rest of today on some general properties of quantum entropy, and then we're going to go back to quantum information in black holes and black hole evaporation. So, quantum entropy. Start with the definition. The entropy of a density matrix rho is minus the trace of rho log rho. Now, if rho were a probability distribution, this would be a classical entropy, but rho is a matrix, so it's a quantum entropy. This is the log of an operator, which is kind of a funny thing, but you can think of this as being the sum over eigenvalues of lambda I log lambda I, and then it feels a little bit less funny. Some basic properties of the, so some terminology, I guess. This is called the von Neumann entropy or the quantum entropy. In various other contexts, sometimes it's called the entanglement entropy, or I think I got all of them. I'll refer to by all those names. Some basic properties. It's non-negative. It's equal to 0 if and only if rho is pure. So pure means that I guess I'm not going to prove both directions, but let me just convince you this is true. Pure means that you can write the density matrix as psi as a projector. And that means that we can pick a basis where this is 1, 0, 0, etc. Just by choosing a basis where that first entry is the psi operator, is the psi state. And so the entropy of this state is minus 1 log 1 minus the sum of 0 log 0. 0 log 0 is 0. 1 log 1 is also 0. So it's 0. The entropy is bounded above. S is less than or equal to the entropy of it's bounded above by the entropy of the maximally mixed state. Okay, so a maximally mixed state is the state that's proportional to the identity. But we're talking here about normalized density matrices. Okay, so they need to have trace 1. So the maximally mixed state is the identity times 1 over the dimension of the Hilbert space. So this is the maximal entropy that you can get in Hilbert space H. Of course, we're going to be talking about quantum field theory, and in quantum field theory, the Hilbert space of any quantum field theory or any region or Q of t on any space is always infinite. So this is always going to be infinity in Q of t, and that's going to be important. Of course, as usual, you shouldn't think of it as really being infinity in Q of t. You should think of it as being UV sensitive and to have contributions coming from near the cutoff scale. Of course, it's not really infinity. It's whatever the cutoff scale is. Yeah.
But even for a single harmonic oscillator, the Hilbert space is infinite dimensional.
Yeah.
So if you're just cutting off like at high frequency, then you're saying, well, some of these modes don't exist in a Hilbert space, but the lower modes still have infinite Hilbert spaces.
The lower modes have infinite Hilbert spaces.
If you're saying, like in a free theory, there's a harmonic oscillator for every mode.
Yeah.
And then if we impose a UV cutoff, we're saying we're going to exclude some of the modes. But the
there's
lower
really
modes are
there's
still
really two
harmonic.
things going on here. So it's true, the harmonic oscillator has an infinite dimensional Hilbert space, but any reasonable states that we talk about in the harmonic oscillator only populate some. Well, that's not true. Coherent states populate all the way up. Okay, in quantum field theory, even the vacuum state is going to have infinite entanglement. So that's really what makes this important. I mean, this statement about the maximum, this can be refined. So like, it's really bounded above by the number of important states. So, for example, if you're in the harmonic oscillator at some finite temperature, there's only so many of those states are going to be important, and it's going to be bounded above by that. So there's a refined version of this. But I don't want to, we're going to get into the examples in QFTs. Okay, another property is that if you have an operator V, so I'll define this in a second. If the operator V is an isometry, then S of V rho V dagger is equal to S of rho. So an isometry is kind of like a unitary, but an isometry can map to a bigger space. So V maps H to H prime and satisfies V dagger V is equal to 1. So an isometry is a map whose dagger undoes itself, which is undone by its conjugate. We're used to thinking about unitary operators that do that, but an isometry is a more general thing. A couple words of interpretation of the entropy. Well, there's many different ways of interpreting the entropy. I'm just going to give one for now, I think. Yeah, I'm just going to give one, which is kind of my favorite for our purposes. The von Neumann entropy of a density matrix rho A is the log the number of states required to purify row A. This is approximate. Okay, S is continuous function. Numbers are not continuous. Number of states are not continuous. This is just a useful way to think about it for the kinds of applications that we're going to discuss. So we know that any state can be purified, and this is just telling us that how to interpret that in terms of the entropy. If you have a Hilbert space that factorizes into HA times HB, I think I mentioned this at some point, but here it is again, then you can define reduced density matrices on subspaces by doing partial traces. So if we have a density matrix on the full Hilbert space, we could take a partial trace over B and get it on the factor A. And so in situations like this, where you have traced some stuff out, S of row A is often called the entanglement entropy. A caveat here is that it only really makes sense to call it the entanglement entropy if the full state is pure. Okay, so for example, we could take a state in this Hilbert space, which is just the thermal state in row A times the thermal state, the thermal state in A times the thermal state in B, and of course the von Neumann entropy of this state in A will be the thermal entropy, but it has nothing to do with entanglement. It's completely unentangled. Okay, so caveat, or I don't have to make it a caveat. Let's just say it measures entanglement if row AB is pure. Actually, I didn't think to write this one in my notes, but this is an important one. S of the thermal state, which is the normalized version of e to the minus beta h. S of a thermal state, the von Neumann entropy of a thermal state is equal to the thermal entropy at that temperature, inverse temperature. In fact, one way to think about the thermal entropy is that it's defined this way. Okay, so okay, let me pause and make this distinction, which I wasn't planning to say now, but let me see if I can say it clearly. So the quantum entropy is a fine-grained entropy. It's telling us if we know the exact density matrix of a quantum system, there's an entropy assigned to that exact density matrix. That's what it means to be fine-grained. So like, if the atoms in this room were in a pure state, they're not because they're hitting the walls and stuff. But if they're in a pure state, like say we measure them. Say we measure where every atom in this room is, in the air in this room. We measure it. Now we project onto a pure state. We have the state. The fine-grained entropy of of the air in the room is 0. As thermal entropy doesn't care that we just measured it. The thermodynamic entropy of the air in this room is determined by thermodynamics, and it's only a function of the temperature. It doesn't care if we happen to have measured where all the atoms are. Okay, so that's a coarse-grained entropy. So it's going to be very important for us to distinguish between fine-grained entropies, like the quantum entropy, and coarse-grained entropies, like the thermodynamic entropy. One way of thinking about coarse-grained entropies is that they come from maximizing the fine-grained entropy subject to some constraints. So one way of deriving the Boltzmann distribution, e to the minus beta h, is to say you want to find the density matrix that maximizes the von Neumann entropy subject to fixing the energy. The usual thermal ensemble is the density matrix that maximizes the von Neumann entropy subject to constraint on that. And other kinds of coarse-grained entropies are just defined by putting in other constraints. For example, we could constrain the charge or other things like that. Okay. The entropy obeys subadditivity, which says that S of rho AB is less than or equal to S of rho A plus S of rho B. I'm not going to prove that, but it's true. If you have complementary subsystems, that just means like this situation that we were just talking about with entanglement entropy, where H is the product of HA times HB. If rho AB is pure, then S of rho A is equal to S of rho B. So in a pure state, the entanglement entropy of complementary subregions are equal. There's a quick proof of this. I don't know if this is totally obvious. I'm used to it, so I don't think it's obvious from looking at the formula, unless you think about it the right way. So let me tell you how this is proved briefly. The proof is to use the Schmidt decomposition. So the Schmidt decomposition says that any state in a factorized space like this can be written as the sum from I equals 1 to n of lambda I in A, I in B. With n less than or equal to the number of states you have to keep in the Schmidt decomposition is the smaller of the two Hilbert spaces. So min of DMHA, DMHB. So in other words, if you can have, say you have like, I don't know, let me come up with an example. say you have like 1 qubit. You're doing some quantum computing here in this room, not recommended, room temperature. But you're trying to do some quantum computing in this room. You have your 1 qubit, and it gets entangled with the air in the room. Okay, so now let's do the Schmidt decomposition. So what it says is that there's a choice of basis in which that 1 qubit that you're holding, so that's our region A, is entangled with one particular state of the air. Now, that's a statement about one particular, there's a choice of basis where that's true. So that you can write it this way. So if it's pure, then there's one particular state of the air that you can put here and get this decomposition. And once you have this, the statement about complementary subsystems becomes trivial, because this Schmidt decomposition, now we can use this to write rho A. Rho A is the sum over I of lambda I squared IA, and rho B is the sum over I of lambda I squared IB. But these two density matrices have the same eigenvalues and therefore the same von Neumann entropy. So we're done. Schmidt decomposition is also the way to think about this this interpretation that I gave you. I said that the von Neumann entropy tells you how many auxiliary states you need to purify a system. And so that's the same kind of argument. Next property, strong subadditivity. Affectionately known as SSA. So this is when you have 3 different subsystems. So there's a product HA times HB times HC. In this situation, the von Neumann entropy obeys S of B plus S of ABC is less than or equal S of AB plus S of BC. I've changed notation a little bit here. I got tired of writing subscripts. S of A just means S of rho A, etc. There's a lot of different ways to think about SSA. One way to think about it is in terms of what's called the monogamy of entanglement. So things can't be entangled. They can only be entangled with one other thing. That's called the monogamy of entanglement. So if you have a qubit that's maximally entangled with another qubit, it can't also be entangled with anything else. And what SSA does, or one thing that SSA does, is it quantifies that relationship of how strongly things can be entangled with multiple parties. I'm not going to explain that in detail right now because we're going to come back to it. This is very important for the information paradox because, as I think I at least hinted at some point, the information paradox is sort of a problem that comes from the fact that the Hawking radiation that's escaping the black hole wants to be like, you need it to be entangled with two other people. You need that Hawking mode to be entangled with the black hole interior, for the horizon to be smooth. But you need that Hawking mode to be entangled with the other radiation for the radiation to be pure. Okay, so SSA and the information paradox are closely related. I'm gonna introduce a couple of other information-y quantities because they're useful. So, another pen. Yeah.
Sorry, I have a question about this earlier statement. So about this on the right side of the bottom. So fixed energy is the microcanonical ensemble, right? And then the density matrix you have above that is canonical ensemble. Does it matter, or because of the thermodynamics of it, extremizing?
Yeah, the canonical ensemble doesn't fix the energy. It fixes the expectation value of the energy. So the canonical ensemble is the density matrix that maximizes the entropy subject to a fixed expectation value for the energy. It includes all energies. So one other thing that's useful to talk about is called the relative entropy. The relative entropy is a comparison between two density matrices, rho and sigma. And it's defined to be minus trace of rho log sigma plus trace of rho log rho. I'm not going to go much into the relative entropy. I'll just say that it measures distinguishability. Of two density matrices. There's a detailed version of that statement which basically says that you can use the relative entropy to determine how many measurements you have to do to tell these two density matrices apart. As a quick little application, let's look at the relative entropy of rho compared to the maximally mixed state, proportional to the identity. So according to the definition, this is minus trace of rho log 1 over n. The second term in the definition is just the negative of the von Neumann entropy, so minus S of rho. So this is the log of the dimension of the Hilbert space minus S of rho. And you should think of this as a measure of information content. Okay, the maximally mixed state has no information in it. It's just everything is completely mixed up. There's no information whatsoever. So the distance from the maximally mixed state in terms of relative entropy is like how much information you have in the state. And the reason I give this example is because it gives another way of thinking about the entropy. Okay, so the bigger the entropy, the further, wait, it's back, do I have backwards? Yeah, the information content is log dim h minus the entropy. So if we put if rho is maximally mixed, then these will cancel and we'll get 0. As as the entropy goes down, there's more information in your state. So the relative entropy has a lot of nice properties. A sort of essential one is the monotonicity of relative entropy, which says that the entropy of rho A slash sigma A is less than or equal to the entropy of rho AB slash sigma AB. This is kind of obvious if you believe me that the relative entropy is a measure of distinguishability. Because if I have states rho and sigma, and they're distinguishable, they're certain distance apart, there's certain difficulty to distinguish them. But if I just don't look at part B, if I don't look at region B, it can only get harder to distinguish them. That's what this inequality says. So this is a very natural inequality. Monotonicity of relative entropy is actually more general than this. It's monotonic not only under partial trace, which is this relationship, but under lots of other things that you can do to a density matrix. But I don't think we're going to have use for the more general one, so I didn't introduce it.
Tom?
Yeah.
The expression for relative entropy is not symmetric in rho and sigma.
That's true, yes.
But your interpretation that it is a measure of distinguishability between two states is like a symmetric argument in rho and sigma.
Well, no, if I really if I really told you what this means, then it would not be symmetric. Let's see if I remember the exact.
It's more like a hypothesis test. It's like if you
Yeah.
assume that it's sigma, then like
Exactly.
every row, like can you like reject the null hypothesis that it's sigma?
Yeah, thank you. Okay, I think the last one for now, yes, the last one for now is called the mutual information. So the mutual information, I of A and B, is S of A plus S of B minus S of AB. And if you look at if you go through the definition of relative entropy, you can also write this as S of rho AB with respect to rho A times rho B. The mutual information measures correlation between the two subsystems. It measures both classical and quantum correlation. The mutual information is non-negative. We've already seen, that's the third time we've made that statement actually. Okay, so the subadditivity inequality is positivity of mutual information. But relative entropy is also non-negative. So again. And the mutual information also gives us a nice way to think about strong subadditivity. So the strong subadditivity inequality, rewritten in terms of the mutual information, is I of AB is less than or equal to I of A with BC. If you accept that the mutual information measures the information that's mutual, then this seems pretty obvious. But I guess I should have said that strong subadditivity is a very deep thing, and it's actually very hard to prove. It took people years to prove strong subadditivity. It's just a statement about matrices. It's very hard to prove, and the proofs are terrible. They're really kind of rough. I mean, they're not terrible. You can read them, but they're not easy. Strong subadditivity. So this is also, of course, a statement about relative entropy, and in fact, this is monotonicity in disguise, because you can write this as S of rho AB with respect to rho A times rho B is less than S of rho ABC with respect to rho A times rho BC. So it's monotonicity under tracing out C. Okay, that was just really a bunch of definitions, and yeah, go ahead.
Can I add one little piece of information that I find interesting? So people often define entanglement measures based on certain properties like monotonicity and a few other things that we want all entanglement measures to satisfy, and then you can prove that any entanglement measure on pure states is equal to the non-Neumann entropy.
I see.
Where
Okay, yeah, it's
equal
yeah.
up to some.
Uh-huh. That sounds reasonable. Yeah, that's often this trace of rho log rho, it feels weird. It feels like a weird equation to write, but even in thermodynamics, you can put in some very basic things you'd like entropy to satisfy and show that it basically has to be that equation. That I can't really remember exactly what the inputs are, but it's kind of the only reasonable thing that obeys the requirements you'd like entropy to obey.
Tom?
Yeah.
So, because you are saying that mutual information measures both classical and quantum correlations, we cannot use it directly to characterize just entanglement, right?
Correct.
So
Correct.
how is it useful in our context?
Well, I mean, we'll see, but it gives us strong subadditivity, for example.
Yeah, that is yeah.
Okay, and that is sort of a inequality on who can be entangled with who. Yeah. I mean, I don't know if I'm not sure I'm going to use mutual information. I might just use strong subadditivity, but they're sort of related. So. Okay, so this was just a bunch of definition. Yeah, sorry, go ahead.
I was a bit confused about the measure of information content part because the formula indicates that if S is lower, then the information content is higher, and I'm just confused how low. It doesn't intuitively make sense that lower.
I think it makes sense in the sense that if I gave you a book as opposed to like a maximally mixed set of ink particles, the book would have lower entropy than the other one. So the way you store information is by making something not random. That's how you store information in an object, is by making it not be maximally mixed. Yeah. Does that help?
Yeah.
Yeah.
Earlier you mentioned knowing every air particle in the room and the difference between the two entropies.
Yeah.
If you know every particle in the room, I'm a bit confused why the thermodynamic entropy wouldn't also be, because you can relate that to the Shannon entropy, and then you know the states of the room, and so it feels like it should not be, it should also be the same as.
Well, I guess it depends a little bit what exactly you mean by thermodynamic entropy.
Yeah.
But what I meant by thermodynamic, this is terrible. I really meant thermodynamic entropy, which is a function only of temperature. S of beta, call it S thermal of beta, is 1 minus beta d beta log z of beta. And the thing I said in words, let me attach an equation to it, is that this is the max over, let me write the rest first. This is the max von Neumann entropy, S of rho, where you maximize over all density matrices rho, such that trace of H rho is equal to E of beta, the energy at temperature beta. So in other words, what I'm calling thermodynamic entropy is pretty much by definition the entropy that forgets all the details.
Okay, so you're just pretending like that you don't know the locations. You're just pretending.
Yeah, but I would say that's what we mean by thermodynamic
Okay.
entropy.
Okay. That makes sense.
I think what we really mean by it is it's a state function that depends only on a few macroscopic quantities, energy, whatever, temperature.
Okay. And it can be related to like the information theory entropy by that formula, basically.
Yeah, exactly. Okay, red seems to be doing better, so now I have to shout at everyone for the rest of the lecture with this red ink. Okay, so now I want to talk about entanglement entropy, and in particular subregion entropy as it appears in physics. Okay, by physics I mean like physical systems with a Hamiltonian and whatnot. As opposed to just manipulating qubits on a quantum computer. So we're going to start with quantum mechanics, and then we're going to quickly jump to quantum field theory. But some of the concepts are similar. So consider n spins in a row. Okay, so just imagine that we have a bunch of spins sitting next to each other that are coupled in some way, which is why I drew the lines between them. And this isn't really necessary, but just to keep things a little easier, I'm going to put periodic boundary conditions on my n spins. The Hilbert space of this chain is the span of the states sigma 1, sigma 2, dot, 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 sigma n, where these, each of the spins is either up or down, which I'll call 0 or 1. Okay, so you can think of them as spins or think of them as qubits. This basis, where you just give them all zeros or ones, is often called either the classical basis or the computational basis. When we were talking about quantum field theory, it's what I call the field basis. It's like you have a particular phi of x in space.
Sorry. Except now we're talking about spins instead of.
Yeah, I mean, it's analogous. Yeah. Okay, so the most general state you can write, pure state that you can write for this chain, is a sum over all this set of sigma i's of some function that depends on all the spins, and the state. Okay, so we can expand in this basis, obviously. Now, let's think about how much information you need to store this. Okay, so you want to store this on disk. So how much information are we talking about? Well, this is 2 to the n complex numbers. Okay, so the quantum state of something with n spins is enormous. It grows exponentially with n. If you get up to I don't know how high I have to get before you can't store this on all the disks in the world, but it's not that high. It's less than 100. Quite a bit less, I think. Now, we want to talk about subregions. So let me define a region A. Yeah. Okay, so this is region A, and region A consists of L spins in a row somewhere on the chain, where for now L is much less than N. Now, in most pure states, of the full chain, the region A is maximally mixed. Okay, so that's like if you took the air in this room and you just took like a little bit of it, then that little bit would be in a maximally mixed state because it's entangled with everything else. So in most pure states, rho A is proportional to the identity on A, and that means that the entropy of A, we expect in most states goes as, or is very close to L log 2. I'm going to quantify this next time and say what I mean by most pure states and that sort of thing. But for now, let's just say it's sort of obvious that if you take a tiny subsystem, it's going to be entangled with everything else, so it's going to be mixed, maximally mixed. So this is called volume law entanglement. Because L is the volume. L is the volume of region A. And we said that in most pure states, the same is true in most mixed states. That's going to be even more mixed. In most states, period, the entropy of a subregion is volume law. The way you should think about this on our picture here is that each of these qubits can be at most log 2 entangled. Like if you take a qubit and you maximally entangle with something, you get a log 2 in the entropy. So each of these can produce up to log 2 of entanglement. If it's mostly entangled with other stuff in region A, that will not contribute to the entropy. Like if there's some entanglement between neighboring guys, both in region A, that will not contribute to the fine-grained entropy because together they're pure. But if it's entangled with something outside, or a whole bunch of stuff that's outside, that will contribute to the von Neumann entropy. So typically, it's entangled with stuff outside, and we get volume law entanglement. However, in the ground state of a local Hamiltonian, so the point I want to make is that ground states of local Hamiltonians are very special. And they don't have volume law entanglement. In fact, they have area law entanglement. And this is crucial. So in the ground state of a local Hamiltonian, correlations are short range. Meaning, if you calculate some correlation function of operators on sites I and j, then this will go to 0 as I minus j gets large. In other words, in the ground state of the local Hamiltonian, a spin is only entangled with nearby spins. That's what it means. That's what this means. That's what that indicates in terms of entanglement. Entanglement is local. And what that means about the quantum entropy is that if you calculate S of A in this ground state of a local Hamiltonian, then there's two things that commonly happen. The first thing is that you get a constant. Meaning not a function of L, meaning independent of L. Okay, so as long as it's much smaller than the whole system. The other thing that can happen is this can be slightly violated, and you can get log L. The distinction between these is the distinction between well, it's sort of a difference of how long range the correlations are. So, in fact, the constant is what you get in gap systems, where correlation functions die off exponentially. The log L is what you get in ungapped systems, massless systems, where the correlation functions die off as power laws. I believe in one dimension that this is a theorem. I didn't exactly state it precisely, but I believe it's a theorem that ground states of local Hamiltonians have this very special structure of the entanglement entropy. in higher dimensions, it's not a theorem, but it's still true. So in higher dimensions, in the ground state, S of A goes as the area of A. In one dimension, that's just a constant. The area of an interval is just 1. There can be logarithmic corrections to this, so it can go as the area of A times log of the size. And that would depend on the details. So the point is that ground states of local Hamiltonians live in a very special corner of Hilbert space. Yeah.
Is this a bound? Because if I take something like a ferromagnet, meaning number of dimensions, then there are only 2 ground states, all spins up or all spins down. And so it seems like when I increase the size of A, it doesn't increase the entropy.
That's true. That's a good point. Let's see. I guess it's a bound, but it's true whenever the system is interacting. You know, the reason that the model you're talking about seems to have nothing interesting going on is because there are no correlations whatsoever. Like if you add a hopping term to your ferromagnet, I think it will not be area law.
Why are there no correlations at all?
Well, if you add a hopping term, there will be correlations, and then it will be area law. I think when you say ferromagnet, you're just talking about like free spins in a B field. I think maybe that's what you're really talking about.
No, I'm talking about no B field and where you have nearest neighbor ferromagnetic interactions.
Well, the ground state still has no entanglement if it's just a product state of all of this stuff.
Yeah, but is it area law or is it just 0?
Well, it would just be 0 if there's no entanglement.
Well,
there
there's
are
no
two
entanglement.
possibilities, right?
Yeah.
Either the all spins or the ball spins.
Okay, yes.
Yeah.
I mean, that in the one-dimension case, it seems to support that because it tends to a constant. But in higher dimensions,
Yeah. Okay, I'm confused. I got to think about that. My feeling is that it's because you're thinking about a free model, and that
Maybe because there's long range.
long-range correlations.
Yeah, long range. Maybe if the ground state doesn't have long range order, then you do get this area law.
Aha.
Because that assumption you're making in correlations is short range.
Right. Although, yeah, you might have thought it would go the other way, but yeah, that sounds right. Let me think about that. Yeah, I think you're right though, that we have to think about that to make a precise statement.
I have another question.
Yeah.
What if we were talking about a fermionic Hamiltonian? Then the Hilbert space isn't really a tensor product of the different fermions. So like you could have a Hamiltonian that's local in terms of fermions. But then
I mean, because they're some kind of string operators.
Yeah.
Yeah. As long as there's a way of writing the Hamiltonian as a local Hamiltonian, it will have this property.
But I'm
I
wondering.
agree it's not obvious in the other basis why that happens,
But I'm wondering if like if it's local when you write it in terms of spins, then like the spins aren't really things that you could you can't consider the reduced density matrix for a spin. Or sorry, I meant for a fermion. You can't consider the reduced density matrix for a fermion. Because the Hilbert space isn't a tensor product.
Okay. I'm not sure what you're saying though.
I'm wondering whether these results would still hold. Since
I don't know. I guess we'd have to. I'm gonna have to ask exactly what you mean by that, but I think I'm gonna stop here for today, and we can talk after.